Hello and welcome to Chapter 13, which details the lives of stars from birth through middle age. The interstellar medium is all matter between stars. It contains at least 10% of the observed mass of the galaxy, and more than 190 different types of molecules with as many as 70 molecules bonded together have been discovered. 90% of the particle number in the interstellar medium is hydrogen, 9% is helium, and 1% is metals, while 74% of the mass is hydrogen, 25% of the mass is helium, and only 1% of the mass is metals. Where I want to remind you that metals constitute anything that isn't hydrogen or helium. New stars form from the gas and dust of the interstellar medium, which marks it as places to look for young stars. The bluish haze starlight scattered by the interstellar gas and dust is called the reflection nebula. A nebula, plural nebulae, is a dense region of interstellar gas and dust. Nebulae are embedded in much larger bodies of gas and dust called molecular clouds. The largest molecular clouds, called giant molecular clouds, contain upward of 1 million solar masses of matter and extend up to 600 light years across. Dark nebulae are sufficiently dense to prevent most of the visible light behind them from getting to us and look like areas of empty space. This darkening is called interstellar extinction. Interstellar reddening occurs because dust scatters short wavelength red light more than longer wavelength light. Emission nebulae glow from the energy received from nearby stars, from exploding stars, and from collisions between nebulae. A supernova is a violent detonation that ends the life cycle of a massive star. Supernova remnants are another type of nebula which pass through the interstellar medium and collides with existing matter, causing the gases to glow, and possibly, if fast enough against a giant molecular cloud, can compress the star cloud and make it genes unstable, marking the birth of a new star. Collisions between two interstellar clouds and ionizing radiation from O and B stars can also cause genes instability. As regions become denser, they block light from behind and appear dark with dense cores inside destined to become stars. These are called bulk globules. At first, a collapsing dense core is just a cold, dusty region thousands of times larger than our solar system. The dense core actually collapses from the inside out. The inner region falls in rapidly, leaving the outer region of the dense core to drift in at a more leisurely rate. This process of increasing mass of the central region is called accretion, and the newly formed object at the center is called a protostar. Protostars emit energy from the compression and heating of its interior caused by the gravitational force. If a dense core is not spinning, it becomes a singular sphere, which becomes an isolated star. But if it is spinning, it collapses into a disk, which may become many stars. When mass accretion stops, the protostar becomes a pre-main sequence star, which contracts slowly and begins fusion when the temperature at its core reaches 10 to the 7th Kelvin. Stopping its contraction as the energy released creates pressure opposing the contraction. The outer shell of gas and dust finally dissipates and the star emits visible light to the universe. The more massive a pre-main sequence star is, which is what these stars that come about are, the more rapidly it begins hydrogen fusion at its core. For about 5 solar masses, pre-sequence main sequence stars start fusing within 1 million years, whereas for about 1 solar mass it takes a few tens of millions of years. Stars less massive than 0.08 solar masses do not have enough gravitational force to start hydrogen fusion and become brown dwarfs. The least massive star to be observed is 0.091 solar masses, only 95 times more massive than Jupiter. These brown dwarfs can still sometimes fuse deuterium into helium or lithium into helium, but this is relatively short-lived as there's relatively little of this material. Here you'll see the evolutionary tracks of different masses for main sequence as they become main sequence stars from pre-main sequence stars. And what you'll see is that this is more of a gradual decrease down the HR diagram as you start out with large stars such as the 15 solar mass star at the top, whereas it is a very kind of violent decrease down in the red region down and to the left as you start out with zero point 0.5 solar mass star. You can also tell the ages of stars by the density of the number of stars at a certain area along the main sequence, where more stars in one area means that the overall stellar neighborhood or the celestial neighborhood or whatever you want to call it is going to be closer to that age. Main sequence stars are those stars in hydrostatic equilibrium with nuclear reactions fusing hydrogen into helium in their cores at a nearly constant rate. The location on the HR diagram where this happens is the zero-age main sequence, which is given by the blue lines in the previous HR diagrams that we were looking at. Going through this process, it starts with the first picture where in this cold dark nebula, gas atoms and dust particles move so slowly that gravity can draw them together. Gas and dust begin to condense into clumps, forming the cores of protostars. As the cores condense, their density and temperature both increase. As the protostars continue to heat up and accrete matter from the nebula, they begin to glow due to their increasing temperature. If the core is rotating, some gas and dust in it form a disk around the protostar. When accretion stops, the protostar becomes a pre-main sequence star. Its core heats to 10 to the 7th Kelvin, and fusion begins there. In the Tauri stage, the young star ejects mass into space in opposite directions. The stellar wind blows away the remaining parts of the nebula that surround the star, exposing the star to space. The ejected mass can induce a shock wave in the surrounding interstellar material, triggering the formation of additional stars, or processes that cause the star to lose or gain mass come to an end, and the star stabilizes as a main sequence star in a hydrostatic equilibrium. A system of planet often forms around the star and the disk of gas and dust. You should take some time on your own to look at these different surface temperatures, luminosity, time on the main sequence, and spectral classes for different solar masses of main sequence stars. Masses between 0.08 and 0.4 solar masses become red dwarfs. They're the dimmest of all main sequence stars and fully convective, where hydrogen will be pulled in towards the core and helium will be pushed out of the core and eventually pushed out of the star itself, leaving a completely hydrogen-based star. So they are about 85% of all stars in our galaxy. When core hydrogen fusion slows down, main sequence stars with mass greater than 0.4 solar masses become a giant. Not fully convected, chemical composition of their cores differ from the composition of their outer layers. As the rate of this fusion decreases, the star can no longer support the crushing weight of its outer layers, and so the hydrogen-rich gas just outside the core is compressed inward and thereby heated enough to begin fusing into helium. This process is called hydrogen shell fusion because it occurs in a shell a few thousand kilometers thick surrounding its core. Photons first created in the shell have more energy from which to push the outer layers outward than do photons from the core, which created closer to the star center have to hold out more of the star's mass. In other words, the core photons have lost energy by the time they emerge from the core, so they cannot push the outer layers as much as can the shell photons. The outer layers of stars with shell fusion therefore expand farther out. The stars become larger than they were in the main sequence. They are lower temperature but more luminous. Here we have a diagram showing the evolution of a main sequence star to a young red giant to a red giant, where it starts with a hydrogen fusing core, which creates helium, which is going to be a helium core with a hydrogen fusing shell, until the helium starts fusing in the core itself and it becomes a more intermediary size between the young red giant and the main sequence star size. For lower solar masses between 0.4 and 2 solar masses, the helium cores are solid and completely ionized, separated into nuclei and electrons. The Pauli exclusion principle states that these electrons cannot be at the same speed, so they start growing at higher speeds, causing electron degeneracy to pressure, which causes the core to grow. When the degenerate core's temperature increases, the pressure there does not increase without the safety valve of increasing pressure. The star's core cannot expand and cool when overheated. Rather, it sits there, just getting hotter and hotter. Once the core reaches 100 million Kelvin, core temperature helium fusion begins, and the rate of fusion and core temperature increase in helium flash until the temperature reaches around 3.5 times 10 to the 8th Kelvin, when it transforms back into an ordinary gas, which causes the core to expand and cool itself, and the hydrogen shell, decreasing fusion and causing the star to shrink within a few hours. In this slide, we see the luminosity of the sun versus time as it contracts from a protostar, joins the main sequence, and then has its sudden helium flash as a red giant, which causes it to peak and then go down. We also see on the HR diagram the lifespan of these red giants with their as they undergo helium flash and have that kind of discontinuity that you see in the dotted line. With more than 2 solar masses, the gravitational force can compress and heat the core until it reaches the fusion temperature of helium with no helium flash. There is also a triple alpha process where helium-4 or 3 versions of helium-4, which is called an alpha particle, combine to make carbon and a gamma particle, which is just a photon, and then that carbon particle and another helium-4 creates oxygen and a photon. Giant stars fuse helium in their cores for about 10% as long as they spin fusing hydrogen while on the main sequence. For example, the sun will spin about 10 billion years on the main sequence, after which it will be a giant for about 1 billion years. While helium fusion is occurring in a giant's core, further gravitational contraction of the star's core ceases. After core helium fusion begins, the evolutionary track of mature stars move partway back towards the main sequence, right to left on the HR diagram. Their pressure, temperature, safety valves are not perfect, so as they shrink, they overheat and core fusion causes them to expand to larger sizes than they would be at equilibrium. Becoming too large, their pressure and temperature decreases as they collapse, overcompressing and thereby overheating themselves again. This process is analogous to dropping a tennis ball, which bounces repeatedly after striking the ground. In other words, a star under these conditions becomes unstable and pulsates. The region on the HR diagram between the main sequence and the right side of the giant branch where this occurs is called the instability strip. These so-called variable stars can be easily identified by their changes in brightness amid a field of stars of constant luminosity. Lower mass post-helium flash stars pass through the lower end of the instability strip as they move horizontally on the HR diagram along their evolutionary tracks. These stars become RR Lyrae variables named after the prototype in the constellation Lyra. The RR Lyrae variables all have periods shorter than 1 day. Higher mass stars that evolve from the same interstellar medium as RR Lyrae pass back and forth through the upper end of the instability strip on the HR diagram. These stars become type 1 Cepheid variables who often simply called Cepheids. There is another whole group of variable stars called type 2 Cepheids that formed earlier in the history of the universe from gases with virtually no metals. We discuss them shortly. A Cepheid variable has variable brightness because the star's outer layers are cyclically expand and contract. Star would soon stop pulsating without some mechanism to maintain its oscillations. Variable stars have a layer of gas-rich and partially ionized helium with 1 electron stripped off. This gas, absorbing a lot of photons leaving from the core, heats, expands, and pushes the outer layers outwards just as steam raises the lid of a pot. Eventually, the ionized helium layer is spread so thin that photons pass through it. the ionized helium cools and contracts, and the star's outer layer compresses, compressing the interior gases until the process repeats itself. In our analogy with the pot of the boiling water, when enough of the steam inside escapes, the lid falls back and the steam inside begins to build up again. The period of pulsation is related to the luminosity of the star, which can be compared to the apparent magnitude to calculate the distance of a Cepheid using the period luminosity relation. Globular clusters are gravitationally bound groups of old stars. Over time, the main sequence in a cluster gets shorter and shorter. The top of the surviving portion of the main sequence is called the turn-off point. Stars at the turn-off point are just beginning to exhaust the hydrogen in their cores. The theory of stellar evolution enables us to predict how long stars will, with different masses, last on the main sequence before moving toward the giant stage. Therefore, the age of stars currently in the turn-off point is the age of the cluster. Consider the plot for the globular cluster M55 as shown on the left. In M55, stars are just leaving the main sequence. Therefore, according to table 13.2, the cluster's age is approximately 12.5 billion years. Here we see an overview of the lifetime of a globular cluster, where the most massive protostars approach the main sequence, become main sequence stars, while the rest of the less massive protostars eventually become main sequence stars. Then, as time passes by, the more massive more massive main sequence stars begin to become giants, which creates a turn-off point where the age/mass of the turn-off point will give us an idea of how old the globular cluster itself is. The Sun is an example of a young, metal-rich star that was likely formed in an open cluster. Such stars are called population 1 stars. Because their spectra show only weak lines of heavy elements, the ancient stars in these clusters are said to be metal-poor. They were created long ago from gases that had not yet been substantially enriched with heavy elements and are called population 2 stars. In the mid-1800s, French mathematician Edouard Roche pointed out that the atmosphere of two stars in a binary system must remain within a pair of teardrop-shaped regions that surround the stars. Otherwise, the gas escapes from the star of its origin, either transferring to the other star, where the teardrops make contact, or escaping completely from the binary in the opposite direction. Here we see three types of binary stars: a semi-detached binary, where the apparent visual magnitude of the two stars together dips when large Kular star eclipses the smaller one. It dips a lot, and when the smallest hotter star eclipses the large Kular one, it dips a little bit. When you have the second case, where the Roche lobes have a semi-detached binary with mass transfer. Mass transfers flows from the large star to the small one, forming an accretion disk, which means that the small star, hotter star, eclipses the large, cooler ones to a greater degree. And when you have an over contact binary, both stars are about the same size, so all eclipses are about the same size.